This is our third lesson of Dynamics Module 3, where we learn how to solve GCE O-level examination questions. In our first lesson of this module, I've mentioned that there are 5 types of commonly asked examination questions. We have already covered the first 3 types, so in this lesson, we will cover questions involving action and reaction pair of forces. If you have been following my channel, you all have learned the topic on kinematics, where we learn about objects' motion, its velocities, and acceleration. Now in this lesson, I will show you how kinematics and dynamics are applied together to explain everyday life motions. In this diagram, we have a toy box on a rough wooden floor. A child pulls the toy box to the right with a force X. As the box moves to the right, there is a frictional force F between the toy box and the wooden floor. This frictional force acts to the left, opposite to the direction of motion. Question 1. Is F and X an action and reaction pair of forces? State your reasons. First, let's do a quick recap. Action and reaction pair of forces have to be equal in magnitude, opposite in directions, and act on different bodies, and are of the same type of forces. In this case, first and foremost, the force X is not a frictional force. This itself already tells us that X and F are not a pair of action and reaction pair of forces. Moreover, the force X acts on the box. The friction F is a force acted by the floor on the box also. So both forces are acting on the same object, the box. For an action-reaction pair of forces, they have to act on different bodies. So this is another reason why X and F are not an action-reaction pair of forces. The child applies different magnitude of the force X, and the acceleration of the toy box is measured and plotted on a graph as shown. Deduce from the graph the magnitude of the frictional force F. Give reasons to support your deduction. Let's do another quick recap. We have previously learned that when an object is acted upon by 2 unbalanced forces in opposite direction, the object will accelerate in the direction of the larger force. This means that for the toy box to accelerate in the direction of the force X, X has to be greater than the frictional force F. From the graph, we see that the acceleration is greater than 0 only when the applied force X is greater than 1 Newton. Hence, the magnitude of the frictional force F is 1 Newton. Now, if you apply Newton's second law of motion, you will even be able to calculate the mass of this box of toys. This is how you do it. Let's say we pick this point when X is equals to 3 Newton. The acceleration from the graph is given as A equals to 0.5 meters per square second. Applying Newton's second law of motion, the product of the mass and acceleration of the object is equals to the resultant force. The resultant force is calculated by X minus F, and that is equals to the mass times its acceleration. Since we know that F is equals to 1 Newton, and when we substitute the values into this equation, we can calculate the mass to be 4 kilograms. Question 4. If the toy box reaches acceleration of 0.5 meters per square second at time t equals 6 seconds, what is its speed? Now let the speed at time t equals to 6 seconds be v meters per second. Since we know that this toy box accelerates from rest, its initial speed is 0 meters per second. Using the formula for acceleration, we can calculate its speed at that instant to be 2 meters per second. Isn't this very interesting that we can apply our knowledge of both kinematics and dynamics in the same question? Now, since we have learned before that Newton's first law of motion states that an object will continue its motion in a straight line if there is no resultant force. Ignoring air resistance, what do you think you can do to make the toy box continue at the speed of 2 meters per second? The way to do it is to reduce the force X to 1 Newton to be the same as the frictional force, so that the resultant force is 0. Now take note, when the object is not moving and if X is equals to 1 Newton, there is no resultant force, it will not move. But when the object is already traveling at a speed of 2 meters per second at time t equals 6 seconds, when you reduce the magnitude of X to make the resultant force to be 0, the object do not stop. It continues to move in a straight line at the speed of 2 meters per second. I hope you have enjoyed this lesson. Visit my website for more tutorial questions and video lessons. And remember to subscribe to my channel so that you can be alerted when I post the next video lessons.